Alright, so now we will come to how do you choose variables. Okay, we did not have much of a choice in the case of 1D, or we did not spend too much time on it, but so we will have a look at it over here. So, what is called the total field formulation? This will look like a very obvious thing, because so far we have been only talking about total field formulation. So, what does it mean? It means that the variable of interest equals total field, and that is why it is called the total field formulation. So, your H over here can be written as, so H total as H scattered plus H incident. Okay. In scattering problems, H incident is known. You could choose to have your variables be either the total field or the scattered field. It is your choice, it is totally your choice. Each method will have some advantages and some disadvantages. So, the first and the most intuitive choice is allow the total field to be the variable. Okay. So, once I get the total field, if I want the scattered field, I have to subtract of the incident field, and vice versa for the scattered field once, right. What is the, when I choose total field over here, what is the sort of one conceptual simplicity you can see of doing that? Boundary conditions are obeyed by whom? No, the boundary conditions in Maxwell's equations. Boundary condition which is tangential E and tangential H are conserved, they are obeyed by total field, right. So, it becomes easy to impose the natural boundary conditions in the total field formulation, right. So, you can say that easily satisfy, let us call them natural, yeah. So, I am calling them natural Maxwell's tangential boundary condition. Right. Basically, E tan is conserved, H tan is conserved. But on the disadvantage, when I come to the radiation boundary condition, the disadvantage is that this boundary condition which I just derived, radiation boundary condition, it was obeyed by whom? Scattered field, not the total field. So, if my variable is total field, like we had done in the case of 1D, I have to subtract of the incident field and then impose the boundary condition, right. So, slightly harder, not very hard, but we just have to take care of it. Okay. So, let's look at the expression that I had. So, n cross 1 by epsilon del cross H, that was the term that I was struggling with, right. So, what do I do now? So, first of all, I have to write this as n cross 1 by epsilon r del cross H, this is the slightly tricky part, H incident So, I add and subtract incident field, fine. So, what happens as a result of that? First term becomes n cross 1 by epsilon r del cross H incident. This term is known, right. And what happens over here? So, n cross 1 by epsilon r, let us just write it once, H minus H incident, right. This expression remains as it is, and I am left over here with that approximate expression. So, that was what? N cross 1 by epsilon r, and this was replaced by, let us have a look over here, yeah. So, this whole expression over here. So, minus j k by epsilon r. Okay, n cross n cross, the same expression must hold true. Right? Now, in these expressions, there are terms that are known and there are terms that are not known. So, the known terms, for example, I know n, I know epsilon r, I know h incident. So, I can gather all of these known terms and they will become jk by epsilon r n cross h incident. These are the known terms and I am left with minus jk by epsilon r n cross h. Okay. This is just a fancy way of writing what we had already done in 1D. In 1D we had a term, we wanted to impose the radiation boundary condition, we could only impose it on the scattered field. So, how to get the scattered field? Write it like this, h incident plus h scattered. And since my variable is h total, I should not introduce a new hs over here, that will just confuse things. So, this term over here was my h scattered, right, and the rest is just substitution. Okay. So, remember this term was going to coming into play only on the boundary, right, only on boundary. So, this known term over here, this is what is going to give me a non-zero right hand side. Okay. This h over here which has the unknown term, I will move it back to, and when I get Ax is equal to b, I will move this guy back to the left hand side and keep this on the right hand side, right. So, in Ax is equal to b, this term will go back into A and this term will go into B. That is what will happen. So, that is the way with the total field formulation, that is how we will work. Okay. So, it is not tricky, just taking care of on which field I am imposing the boundary condition and so on. So, I will h incident is known, so I will just substitute it over there, and h is the unknown in which I will replace the basis functions. So, we'll in subsequent modules we will go and take a concrete case and see how do I get the system of equations once I substitute the basis function. Okay. So, we'll can we say again? Well, I wouldn't worry about it. So, right now what I have written over here, this expression, this whole thing needs to be dotted with Tm. If you look over here, there is a Tm dot waiting for you, right. So, Tm dot, this is going to be a scalar. So far I have left the Tm out because that is always there like a constant. So, it is going to be a scalar only.